Hello everyone. Today we are going to discuss the problem shortest routes 2 from CSES graph problem set. Let's go through the problem. There are n cities and m roads between them. Your task is to process q queries where you have to determine the length of the shortest route between two given cities. Input contains, the first line contains three integers n, m and q, that is the number of cities, roads and queries. Then there are m lines describing the roads. Each line has three integers a, b and c that says that there is a road between cities a and b whose length is c. And all roads are bidirectional, that is they are two-way routes. Finally, there are q lines describing the queries. Each line has two integers a and b. You need to determine the length of the shortest route between cities a and b. You need to print the length of the shortest route for each edge query, and if there is no route, you simply need to print minus. Okay. And if you look up to the constraints, n can go up till 500, m can go up till n square, q can go up till 10 power 5, and a and b, that is the cities, are numbered from 1 to n, and the weights are from 1 to 10 power 9. So let's first of all try to understand what the problem is. The problem is that you are given several nodes numbered from 1 to n. Let's suppose 1, 2, 3, 4, 5, 6. And there will be q queries. Let's suppose I give you a query 1, 4. This means you need to print the shortest path that exists between 1 to 4. There can be edges like this. There can be multiple edges, and edges will have some weights. Okay. So there will be q queries. Queries will be of this type, like let's suppose 1, 4. This means that you need to print the shortest path from node 1 to node 4. Then there may be a query like let's suppose 2, 3. In this case, you need to print the shortest path from 2 to 3. And if let's suppose the path does not exist, you need to print minus 1. This is what the problem is. Now, whenever these things come into questions, like you need to find the shortest path between two nodes, what all things come to your mind? The first thing that comes to our mind is simply Dijkstra algorithm, right? Dijkstra algo. This is the first thing that comes to our mind. But if you guys remember, when is Dijkstra algorithm used? We have already discussed the shortest routes 1, right? Over there we discussed, over where we solved the problem using Dijkstra. And why was it possible? Because we had a single source. Now, whenever you have a single source and from that particular source you need to find the shortest distance to every other node, Dijkstra come into act. Now just say me one thing. In this particular problem, you may be given any two cities and you need to find shortest distance between those two cities. Doesn't it mean that you should know from a particular node the shortest distance to every other node? Like I should know from node 1 what is the shortest distance to every other node, from node 5 what is the shortest distance to every other node. All these things must be known. So if this is the thing that comes to my mind next is that, okay, Harsh, you are saying that, okay, there are multiple sources. Then why not run Dijkstra for each and every source? This thing comes into mind, right? So let's discuss that thing. Do you guys know what is the time complexity for Dijkstra? It is V plus E log V. Now just say me one thing. If you are running Dijkstra for each and every node, V is the number of vertices and E is the number of edges. If you are running Dijkstra for each and every node, then the time complexity will become V multiplied by V plus E log V. Now you know that for a dense graph, E can go up till V square. You can see in the problem as well, it's given that the number of edges can go up till n square, where n is the number of nodes. For dense graph, E can go up till V square. So can I say that the time complexity becomes, just a minute, the time complexity becomes we go of V cube log V. Can I say this? Right? So if you are using Dijkstra for each and every node, your time complexity will become big of V cube log B. But to solve the same problem, that is from each node you want the shortest distance to every other node, you have a very famous algorithm, that is Floyd-Warshall algorithm. And the time complexity of this particular algorithm is big O of V cube. So this log V factor is not there. So the time complexity of Floyd-Warshall algorithm is lesser as compared to the time complexity of Dijkstra. So the thing that you need to remember is when to use Floyd-Warshall algorithm, when you need the shortest path from every node to every other node. In that case, you use Floyd-Warshall algorithm. Also, Floyd-Warshall algorithm is used when you have negative weights. When the edges have negative weight, in that case, you use Floyd-Warshall algorithm. Dijkstra does not work with negative weight. You guys can refer to this, that why Dijkstra don't work, why Floyd-Warshall work. Yeah, Floyd-Warshall work for negative weights, but it does not work if you have a negative weight cycle. That is, the cycle is there and the sum of weights of all the edges in that cycle is negative. In that case, the Floyd-Warshall does not work. But if there are negative weights and there are no negative weight cycle, the Floyd-Warshall will work. And also, if you want the shortest distance from every node to every other node, this Floyd-Warshall gives you that thing with a time complexity of big O of V cube. So this was the main thing that I wanted to discuss in this problem, that what is Floyd-Warshall algorithm and when does it come into act. How to actually write the code for Floyd-Warshall algorithm, for that I actually would prefer you to see some video for that what is Floyd-Warshall algorithm, how it works, how do we write the code for this. This is not the main this is not the main concern for this particular video, but yes, if you guys know what is Floyd-Warshall algorithm, this video will teach you that when to actually apply it. I would give a bit of context for what Floyd-Warshall is, though I am not going to explain the entire algorithm in this particular video. Can definitely make a separate video for that. So in Floyd-Warshall algorithm, what you do is, you need to find, let's suppose this is particular node V1 and this is particular node V2. Now, from V1 to V2, if you want to calculate a minimum distance, there can be multiple intermediate nodes, right? There can be node 1 via which you are passing. There can be node 2 via which you are passing. There can be node 3 via which you are passing. So there can be multiple intermediate nodes, and what you do is you traverse over all the intermediate nodes and calculate the shortest distance between node V1 and V2. First of all, let's suppose you assume that node 1 is the intermediate node, then shortest distance is distance from V1 to 1 and then 1 to V2. If you assume 2 is the intermediate node, then it's the shortest distance from V1 to 2, then 2 to V2. This is a very high level of what Floyd-Warshall is. You have to see in detail for actually how Floyd-Warshall works. But if you want to find the shortest distance from any node to any other node, Floyd-Warshall algorithm is something that will definitely help you out. So let's see the code for this. So this is the code. First of all, I am taking inputs of nm and q, calculating a 2D vector distance n comma n. So distance ij will tell me the shortest distance from I to j and initializing it to a very big value, that is infinite 2080. Now from every node to reach to the same node, the distance will be 0, right? From 1 to 1 the distance is 0, from 2 to 2 the distance is 0. So I traversed over all i's and distance of I am marking it as 0. Now you take the inputs for edges, you take the inputs for a and b and the weights c. Convert it to 0 based indexing. Distance of AB, distance from A to B is minimum of whatever the current distance is, comma this particular weight, right? Because there is a direct edge from A to B that has a weight of C. So whatever is the minimum distance from A to B currently, comma C. And since it is given that it is a two-way road, basically the edge is bidirectional. So distance from A to B will be same as distance from B to A. So I'm updating the distance of B to A as well. Now I traverse over all the intermediate nodes, traverse over all the cities from I equals to 0, I less than and I plus plus, j equals to I plus 1, j lesser than and j plus plus. If distance of I of k is infinite, then I simply continue. If I am saying that I want to calculate the shortest distance from I to j with k as the intermediate node, then there must be some path that exists from I to k and k to j, right? So if distance of I to k is infinite, this means you haven't updated this distance yet. This means there is no path from I to k. In that case, you are simply continuing. Then going over all the j's. Now, if you just notice, I have started my j from I plus 1. Now, again, if you study Floyd Warshall, you will understand this, why I am able to do this. Because in the current question, it is given that the graph is bidirectional. So you can start your j from I plus 1. Otherwise, you would have required to start from 0 only. So j equals to I plus 1, j lesser than j plus plus. Again, if from k to j the path does not exist, you simply continue. Otherwise, if from I to k it also exists, from k to j also it exists, let's calculate the distance. The distance will be from I to k plus k to j. This is the distance to traverse from node I to node j via the intermediate node k. And if this value is lesser than whatever the already computed value we have in distance ij, we update it. Now we are updating I to j as well, and we are updating j to I as well, because we know that it is bidirectional. Once you have pre-computed the distance, going over all the queries, taking the inputs of node, converting to zero-based indexing. If the value is still infinite, this means you are printing -1, that is the part does not exist. Otherwise, you are printing the distance. So this was a very classic question of Floyd Warshall. You can this you can say as the implementation for Floyd Warshall algorithm. So it will be a very good practice and a very right time to run Floyd Warshall via this particular problem. I hope all of you understood it. Thank you.